Hello everyone, welcome to Phoenixville Public Library. And we're going to the stars tonight, thanks to Dr. Donald Miller, who is a NASA Solar System Ambassador. It's his second time around here at Phoenixville Library. We're pleased to have him here. Welcome to those of you on Zoom. If you have any questions, comments during the presentation tonight, please type them into the chat and I will relay them to Dr. Miller. So take it away.
All right, thank you very much. Great to be here. Got a good crowd here with us in the building, as well as you said 8 online, which is great.
I have 10 right now
10,
online.
excellent.
So, yep.
So you heard I'm Don Miller. I'm basically a volunteer with NASA. NASA ambassadors. We go around to places like this, to universities, to schools, sharing science. That's really what we do. I'm a science guy. I've been that my whole life. Was an R&D, and now that I'm retired, I get to do this fun job. Okay.
What's an R&D?
What's that?
Research and development.
Research R&D.
Oh, okay.
So I've been doing this for a number of years now. I really enjoy it. NASA gives us lots of training and materials, things, and truthfully I have the carte blanche to do what I'd like to do and talk about things. So this is one basically I made up, okay, because it's a really interesting and timely topic, okay. So we're going to talk about when stars go boom, and they do, and then also there's actually one star, the Blaze star, that's actually going to go boom soon. So now you'll understand when that does go boom, it'll make the news like crazy. Okay, so you're ahead of the curve. Okay, let's see if we can get this to work. All right, come on. It was working.
You have the right screen up?
Probably not.
Yeah.
Let's see. I can't seem to, there we go. Only one PowerPoint is up. So if I say present, there we go. Being that I do love astronomy, I just want to quickly have a talk about highlights for this month in the night sky. We just had the, thanks again.
Yep.
We just had the International Observe the Moon Night. I don't know if anybody was able to come. We actually had a big event down at Westchester University. It was NASA sponsored across the world, actually, and showing off our sister planet, the Moon, which was fabulous. The Orion meteor showers coming up here. And actually, a lot of times you think meteor showers, they always say, well, it's going to happen on this date. Really, showers actually happen over a broad time, but they have like a peak time. And this one actually peak will be around the 22nd of this month. These are actually pieces of Halley's Comet. Okay, when a comet comes through our solar system and passes close to the sun, parts of it break off as it's going along. So there's like you can envision this as like a rope going through our solar system, and that rope contains bits and dust from that comet, even though the comet's right now, Halley's is way out in the solar system. Won't come back until, I forget, probably another 50 years. So when Earth actually goes through that rope of material, that's when you get a meteor shower. Okay, this one's not like the biggest meteor shower of the year, 10 to 20, but if you can get a nice dark night, and the way to watch a meteor shower is you don't have to look anywhere particular. Get a nice Chase lounge or something, or nice something stay comfortable, and you look straight up. It's better after midnight, so it's usually good between like 11 at night and like 6 in the morning. Okay, and that's when, because the Earth, when we rotate and we're going through space, we're sweeping out material. So actually the rotation of the Earth is actually helping gather that material so you actually can see it. We get a few tons of dust from space every day coming through. Saturn's really well placed right now. The only trouble with Saturn is the rings are facing us. It depends on where it is in its orbit versus where we are in our orbit, and it happens every like decade or so. That the alignment is that the rings become almost invisible. So if you look at it in a telescope now, you see a nice ball for the planet, and you see a line through it, which is the rings. Mercury is really one of the hardest planets to see because it's so close to the sun. So you have to wait till it's as furthest from the sun as possible. So if you imagine if this is the sun and this is us, my left hand's us, Mercury has to be like to one side of the sun or the other to be at what we call the greatest elongation. So furthest separation from the sun. So on the 29th, if you look at sunset and you have a good view out to the west, you should see it just above the horizon. It's really hard to see otherwise, but it's cool to see Mercury. Okay? All right. Now you're going to stop. I'm just going to have to go and do this. It's like when you took the one thing off, it seems to have screwed it up for the rest. I don't understand.
That shouldn't be that
It's
way,
frozen.
but
We move now. Okay. Go back. Here we go. All right.
I guess we'll just leave that up there.
I
I
guess
don't-
I'll try to. I can take it off.
Hide floating meeting controls.
Thank you.
Yep.
Still work? No. Every time I do that, it's frozen again.
Never experienced that before. Huh.
So this is the International Space Station. Has anyone seen the International Space Station? Yeah, it's kind of cool when it goes over, right? It's amazingly bright. So when you see it, you'll say, oh my God, what is that really bright thing going across the sky? And it goes pretty fast. It's sort of moving like this across the sky, you know? And so these are actually the times for our area. So on the 15th, you'll see it. So this is the highest point. Unfortunately, this sucks up all my laser points. So this would be 6 in the morning, 5, 10 in the morning. So these are the times. So you have to get up early. It'll be dark, but if you get a chance, it's great to just see it go over. It's
I
kind of
had no
fun.
idea you could actually see it.
Oh, it's easy. It's very easy to see.
Wow.
Yeah, so try to get out. You can go, if you have, I put these QR codes up here. People use them already. If you have your phone, you can just scan that while I have it on the screen, and that'll take you to the site that'll let you basically look these things up. And as I go through, you'll see it on other things. You gonna try
Do you need a
it?
telescope to see it, or you see it with
No, you see it with your eye.
binoculars? Really?
Yes. If you have a telescope and you get lucky enough, you can actually see the solar panels on it.
Ha!
Yeah,
Oh my gosh.
that's pretty cool. This is aggravating. All right, I'm just gonna leave that up there. See if that works, yeah. All right, let's get into the topic tonight. Let's start with stars. You know, we think of stars as being eternal. And on human timescales, they are. You know, I mean, our sun is 4.5 billion years old, and it still probably has another 5 billion to go before it turns into a red giant when it uses up the hydrogen that it's converting into helium in the core. So at that point, Earth will probably be consumed by the sun because it's going to get huge.
So are we gonna be leaving before that happens?
That's the idea. Now, humanity will go somewhere if they can. None of us will.
I know, I mean, the future people.
Yep, future people. Probably most humanity will stay on this planet. This be whoever goes off to the other ones. But so these are different types of stars. Does anyone know what type of star our sun is? They do these weird letters here. So basically, and these are basically red dwarfs. These are teeny little stars. And truthfully, the most abundant star in the galaxy, or any galaxy, are little red dwarfs. These things, they're the little engine that could. They just keep going. These things will go for over 1 trillion years.
Holy smoke.
So they're going to go for longer than the age of the universe. They just keep churning because they're so small. They're burning their fuel very slowly. Our sun is basically a G type star, and so surface temperature of about 5,800 Kelvin. I use, as a science person, I talk in metric units, but that would be about 10,000 degrees Fahrenheit. So we talk about the surface tension, surface temperature, excuse me, of the star. You can see the stars progressively get bigger as you go from left to right. And you can see our sun's here, but look at some of these stars and how just gargantuan they can be. Our sun is nowhere near a big, big star. It's actually relatively a small star. But we actually, if you take into account the red dwarfs, And all the stars in our galaxy, our sun's bigger than the average because it's not a red dwarf. Okay. We talk about the temperatures of stars. They go from cool on the left to hot on the right, so red to blue, okay, is what we're talking about. And as astronomers, what they do is they are going to look at the wavelengths of light. Like, you know, red light is a much longer wavelength, meaning one cycle of the light is the wavelength of the light. So red light takes a longer wavelength than a blue light. And the shorter the wavelength, the more energy it has. So what they'll do is they'll actually, the way they can do this, say, how do you know what temperature stars are? You can measure in different light wavelengths and how bright the star is. So that's luminosity. And that's how we can actually then go back and figure out from physics what the temperature is of the star. These are some ideas. So red dwarfs are really low in temperature on the surface. As I said, ours is a G, so you're looking at somewhere in that range, where the O's can get up higher. There's even some stars, as the final stage of life, they're called Wolf-Rayet stars. Those stars can be 150,000 degrees just on the surface. They're incredible. And these are just some things we look for. You know, when you look at the light coming from these stars, you can actually get sort of signatures. There's like a code we can read from the light that says there's helium in there, there's nickel, there's copper. So we can actually tell what's in the stars. So the powerhouse stars, what's actually powerhouse? They begin their life composed primarily of hydrogen and helium. You know, the Big Bang, or the beginning of our universe as we know it, produced just hydrogen, helium, and just a smidge of lithium, okay, if you look at a periodic table. So it was about 75-25 on mass.
Lithium they have lithium batteries, right?
Yep, lithium batteries, exactly, which will combust if you put them out in the air. So it basically is composed of hydrogen and helium, and then it spends most of its life converting that hydrogen into helium with a process called fusion, where it's actually taking hydrogen and fusing it together. I'll show you briefly what that is. This isn't a college course on nucleophysics, so I'm not going to try to convince you of all the things behind it. But when a star is converting hydrogen to helium, the term we use is it's in the main sequence, meaning it's in the prime of life. Okay. Now, late in a star's life, depending on its initial mass, other reactions can occur, meaning it can produce other elements. Okay, at higher temperatures. So the abundance, like I said, was 75-25 from the Big Bang. Current composition of our sun overall, almost the same, 74 and 24%. So it hasn't changed much, but the core, where the things are happening, has changed a lot. It's 33% hydrogen, 65% helium. Okay, so it's been working for 4.5 billion years converting hydrogen into helium, and so a fair amount of the hydrogen's already depleted in that core. So they don't mix very well between the core and the outer layers. And most of the sun's composition's in that outer layers. So
how do they know what's in the core? How do they figure that out?
Well, you can do it a number of ways. Some of it's theoretical, just figuring out, you know, how this would work out. But also, basically, they can do things with looking at quakes on the sun to see what the composition of the sun is through it, because there are solar quakes. So they can actually,
earthquakes.
like earthquakes, but happen on the sun, okay? And we can sample the outer layers of the sun, and then using models, you can try to estimate what's happening there. I mean, we don't have any way of measuring directly the center of the sun. You know, we just don't. We've got a really cool mission right now that's actually flying through the outer layer of the sun, and that's called the Parker Solar Probe. Have you guys heard of that one? It's one of the most amazing missions ever done by mankind. We're flying that thing in, and it's looping around so close to the sun that the only reason it doesn't burn up is it has this incredible heat shield that's always facing the sun, and it's moving at almost 0.1% of the speed of light when it goes around there. I mean, it's moving so fast, it's just unbelievable. But anyway, so that's what's going to happen when the sun. What happens is as you get more and more helium, helium is a bigger molecule than hydrogen. Density of gases are by how big the molecule is, or the molecular weight is what we'd say. So the core is getting squeezed more and more and more as you get more and more helium there. So the sun's getting hotter and hotter and hotter. Right now it's about 20 to 30% hotter than it was when it first formed. In about 1 billion years, it's going to cook us here on this planet. Okay, there won't be any water left. It's just going to get too hot. Okay, because of this process. So this is actually a really cool diagram that if we were in a college class, I could spend a whole lecture on just talking about it. But what you do is you basically plot the surface temperature in Kelvin here on the bottom, and on the side you have how bright it is. The sun being 1, okay, for brightness. So this is called the main sequence. Down here, these are red dwarfs, okay? So, and then the G-type stars and other stars are in here, and these are some of the stars. Our sun's right where my finger is. And this gives you an idea how long we last, about 10 billion years in this one. These over here are 100 billion years, 1 trillion years, like I was saying. And then up here, you're going to get into the supergiants. That's the ones we saw at the beginning. Those only last for 10, 20 million years. So on the scale of the Earth, which has been around 4.5 billion, these stars form and blow up really fast. Okay? And then this is the graveyard down at the bottom with the white dwarfs. Those are dead stars. Okay? But they have so much heat and mass, they'll take 1 billion years or more to cool down. So this is actually, if you're anyone here is chemistry people?
What do you mean by a dead star? It doesn't do anything?
Yeah, it's no longer, there's no fusion occurring in
No
the core of the
activity.
star. So no activity.
They're just floating there.
Just floating there, cooling down slowly.
Mhm.
Just a really big ball of this stuff.
Mhm.
Okay? So there's 2 different types of process. This would be the proton-proton process, and this is called the carbon-nitrogen-oxygen CNO process. Essentially, just in a nutshell, you're taking, it's not as simple as I take one hydrogen and another hydrogen and stick it together. It takes 2 hydrogens coming together to produce tritium. Tritium then has to produce helium. Then you get another one here, another helium. 2 heliums come together to produce this. These are not stable forms of helium to produce this. And it's a complicated process. It doesn't happen like, if you were a molecule of hydrogen, you could sit down in the center of the sun for millions of years and never fuse with anything else. Okay, it's just a very slow process for each molecule. The thing that produces the energy in the sun is it's just so big. It produces the heat that we get. You can actually produce more heat per unit volume in a compost pile than the sun does in the core. Okay, but the sun is just gargantuan and produces as much heat as it does now. Let me give you an idea that one flare off the surface of the sun that you probably read about, solar flares, one flare going off can release more energy in 1 second than mankind produces in 100,000 years. So the scale of the sun, and it's not even that big of a star, is just, can't even really fathom how big it is. I like to ask a question of people, so if you took all the planets in the solar system and you added them together, the mass of all the solar, so Jupiter, Saturn, Earth, Venus, Mars, put them all into one, how much % of the solar system mass-wise would that be versus the sun? Would it be like 70-30, 80-20?
1%?
You got a 1%? What do we got? What do you got? You in the orange. No?
I don't know.
So
Less than 1%.
basically 99.98% is in the sun. Okay, the planets are just dust, a little bit of dust. Okay? It sort of puts you in perspective, right? Just how big it is. And this, I won't go into that. Let me just mention, so you might say, well, wait, if we're making only hydrogen into helium, where's all the other elements come from? And they come from the fact that big stars have a lot more heat and mass than our sun does. Our sun's going to stop probably at helium, might go 1 step beyond a little bit to carbon. But it's not big enough to go too much past that. So this is how you got carbon, then you can make oxygen and helium. So what big stars will do is they'll keep going through their fuel and they'll keep getting hotter and hotter and producing more and more elements as they go. And when they finally hit the very end of their life, they're just full of a bunch of elements. So all the elements in us you know, carbon in this, the carbon in us, the metal down here, it wasn't in the early universe, it was made in another star. So other stars actually made it, exploded, distributed that through a molecular cloud in space, which then condensed down to form our solar system, and ultimately us. So as Carl Sagan used to say, you know, we're star stuff. And it's true, we are
And you
star
know what
stuff.
else he says?
He said a lot of things.
He showed a picture of us at the Earth, and, you know, way out there, and he said, nobody's coming to save us.
That's right, it's us. It's true. We have the responsibility.
To each other.
Yeah, we do. This just gives you an idea, basically, of, and it gets to when stars go boom. So, you know, this is the mass on the bottom here. So you got planets that are down way over here on the left, and brown dwarfs is a weird sort of thing. It's like between a planet and a star. It was bigger than Jupiter, but it wasn't big enough to turn into a star. Okay, you'd have to be about 20 times the size of Jupiter to become a star. And this is basically what happens at the end. Like this, if you're in about the size of our sun, which is right where my hand is, you're going to end up as a helium white dwarf. This is that dead star called a white dwarf. And I'll talk more about that. And then there's carbon-oxygen white dwarf. And ultimately you get to neutron stars and black holes.
Oh, well, be careful you don't trip
Oh, thank you.
on those wires back there.
Yeah, there's a lot of wires. You know, when I go to grade schools, neutron stars and black holes, that's all they want to talk about. So how stars die. So what happens is it's all about a mass. If the star is not very heavy, so what you'll see here is, so if the mass is less than about 8 times the mass of our sun, then when it dies, it basically, a lot of the outer layers are just thrown off. When I say die again, this is when it's no longer able to produce enough heat. I didn't really get into this because there's limited time, but think of a star as like a balloon, and you're trying to compress the balloon because it's all this gas, and the only thing keeping it up is basically the heat in the center expanding the gas out. So as long as that gas, that heat produces enough force out, and it heats the gas up, then the thing's stable. It's called hydrostatic equilibrium. So the star will sit there for, you know, billions of years, just sitting there burning. But when it finally gets to the end of its life and it no longer produces that heat, gravity takes over. And gravity starts crushing it back down. And that can happen in seconds, okay, once it stops producing the energy. Now sometimes what happens is if it's big enough, it crushes down and it gets hotter and hotter in the center, and it starts then fusing other elements together. You can start taking carbon, you know, and going through the different cycles to produce next element, next element. Unfortunately, you can produce energy from each of those steps until you get to iron. When you hit iron, it's over. It takes energy beyond iron to actually produce the next element. So you can actually release energy by going up to iron, but you can't go past it. Okay? And so you'll get a planetary nebula, and then sometime the sun is basically the red dot on the red line on top is our sun. We're going to end up with, you know, billions of years from now as a planetary nebula, and there'll be a white dwarf in the center. And that'll be the end of the sun. And it'll just sit there cooling off for billions of years. But then if it's, sometimes though, there's stars that are in binary systems. Many stars in our galaxy are in binary systems. So sometimes you get a white dwarf who's died, and it's circling another star. And sometimes that can actually start sucking material off the other star and sort of come alive again. So it's like a zombie, okay? And these produce a type of supernova called type 1a. This is the most violent explosion in the known universe, okay? And you can see right here, this spot here, that's a supernova going off compared to a whole galaxy. It actually can be about the same energy output of a galaxy from one star as it's dying, okay? If it's really big, greater than 8 times, then it can go through and evolve, and it can either end up as, it can just basically go into a titanic explosion and totally kill itself, or it can go into a neutron star or a black hole, okay? And it's not always clear to us what dictates this other than mass, but some stars are, you know, pivoting between those. It depends on how much material it throws off before it gets to the very end. This is an old friend. For some of you may recognize this as the periodic chart of elements. And what this just shows you is a little bit what I was talking about before. If it's in blue, the Big Bang made it. So you got hydrogen and helium and lithium a little bit. And then if you want to say, okay, what about you know, these ones down here? Well, that's exploding white dwarf stars. Merging neutron stars are down here. So all these elements were made by different mechanisms in space, okay, by different processes occurring with stars to produce all the elements that we know of. And if this is like, if you said, well, if I could have a highly evolved star, what it would look like? Well, the core would be iron. Remember, it can't go past iron. So then you're going to have basically silicon fusing and producing sulfur. You got magnesium, neon layer. You got a carbon, helium, hydrogen, and then just a little hydrogen envelope on the outside. So it's like an onion. Yes.
If the elements come from stars, how did they get here to Earth? I know we have elements, right?
That's where the elements came from.
From stars?
From stars.
How did,
Well, what happens is when they blow up, they go back into space. Space is full of a lot of different gases, mostly hydrogen and helium.
but it,
And then those elements get distributed, and then usually it's like another big star blowing up creates a pressure wave.
so they
And
create
that pressure wave,
planets.
let me just finish there. That pressure wave actually collapses that gas and can produce a new star system like ours.
They can make planets from,
Yes, it can.
Compressing.
Yes,
okay,
that's how we think it works.
okay.
Okay. Now, there's a lot of science going on as far as how does that process really happen, and what's the dynamics of it, and how does the clouds start spinning. But that's basically, I think we have the right big story. We don't understand all the little bits. So, terminal state of stars, it can be a white dwarf with a brief nebula, complete destruction, neutron star, black hole. Okay. So, what is a white dwarf? Basically, this is something where the star that started off is not that big, much less than 7 times the size of our sun. And basically, it can produce these, basically it'll end up being carbon, oxygen at most. Heat generation internally, none. There's nothing going on. Heat content, basically, it would be hot because it's collapsed down. It'll be around up to 40,000 degrees. And they estimate, like I said here, 1.5 billion years for a 0.6 solar mass to cool down just to 7,100 degrees. So you think, well, space is really cold, but it takes a long time because there's a lot of mass there that got really hot. Neutron stars and black stars. Neutron stars basically composed of neutrons. Essentially think of this as the atom is neutrons, protons in the nucleus, right? And you have the electrons around. Well, what happens with this is the gravity crushes down everything so that the electrons are actually pushed into the protons. So you end up with all neutrons, okay? So that's a neutron star. And if it gets too massive, then the star basically collapses down to what we call a black hole. The understanding of what a black hole is really a point in space with enough matter that the gravity is so high that light can't escape it. We really don't know what's inside that. You know, and that's a question. Yes?
John Wheeler, his son went to our church,
Mhm.
and I met him.
Did you? Yay. Very good.
Thank you.
You're welcome. All right. I think I went the wrong way. So when stars go boom. There's a whole bunch of different ways you can do this. Hypernova, also called a superluminous supernova. Supernova, 2 flavors, kilonova, nova. I'm not going to try to wow you with all this stuff. If you ever want more details, you've got the QR code. So stellar explosion, 2 basic types. Nova, they can either be something that's non-recurrent, meaning it happens once, or it can be a recurrent event. Okay, so it can happen again and again and again. Causes of this strong explosion, it's on the surface of a dead star. So think of a white dwarf, it's dead. So shouldn't have anything going on, but if it gets enough material thrown on the top of it, it can have a surface explosion that goes off. That new star brightens for up millions of times its normal value. It could be 100,000 times as bright as our sun. as far as stellar explosions, nova, this occurs in a binary system. Basically, we'll talk about that. Supernova, sorry, causes a core collapse. So this is actually different in that rather than being on the surface, it's in the core. Okay, so you've been compressed enough that it's going to basically blow from the core. And this can be billions of times as bright as the sun. Basically, there's different ways to carry out. I'm going to skip that. These are little technical details. So this is like, different ways to go. When scientists look at a star, and they think it's going to go, like they say, well, does it have hydrogen? Yes, no. Does it have silicon, narrow hydrogen? They can go through it. They do this by something called spectroscopy. They can take the light from the star, spread it out. You can look for signals in that light. So this type 1 supernova, this is a nice graphic. Aging companion, so basically you have these two stars that are going around each other. This star already finished its life, ended up as a white dwarf. This star, still living, but it's now getting towards the end, it's turning into a red giant. So getting bigger and bigger and bigger, like our sun's going to do. We don't have a companion. What happens is it gets big enough, and it gets where the outer layers of this get close enough to that white dwarf, the white dwarf starts sucking it in. Okay? And once it gets enough material on the surface, it'll blow. A lot of times when it blows, it'll kick that other star right out of the system. And we have actually seen many stars in our galaxy that are zipping along really fast, and they're just going way too fast to stay in our galaxy. We think this is what happens. They got ejected by a supernova, a nova explosion. So here's your decoder ring, okay? Nova, binary, with one of them being a white dwarf surface event. It's about 10 to 100,000 times our sun in 1 year. Kilonova, two compact orbits merge, like say 2 neutron stars. You get 1,000 times. Supernova, basically this is a core event. That's 100. Each of these goes up by orders of magnitude in power. Hypernova being incredibly big. Luckily, there's no star near us that we think can go supernova. The closest one is a star you probably heard of, Betelgeuse. Okay, wonderful show and character, but that's about 640 light years away. So our thinking is it's going to go supernova sometime soon. Soon means 100,000 years. Okay, so could be tomorrow, could be 100,000 years from now, but it's too far away. Even when it goes, it'll be brilliant, and we'll have quite a show in the sky, but it's not going to be dangerous. All right. So as I mentioned at the beginning, basically for several weeks, supernova's luminosity can rival that of a large galaxy. So you can actually see some of these pointed out here, what they are. I mean, it's really incredible. And the way we name the supernovas really with when they occur, like this was 1998. You start with the letter A, and then you go B and C, and then you keep going. So they keep naming these things. So that's 98 BU. So there was a lot of supernovas that year. So they don't happen very often in one galaxy, but when we're looking across the universe, we can see a lot of them. This is just some of how we actually do it spectroscopy-wise. So massive star, when it goes supernova, and this is basically a composed primary environment. And so basically it releases, the electron and proton go together to produce a neutron, as I was saying before, and you release something called a neutrino. This is just showing what happens. So a lot of times with these stars, we think what happens when they collapse is the center becomes a neutron star. Well, neutron stars are the densest material in the known universe outside of a black hole. So when those outer layers come down and they're collapsing here, I'm going to kill myself with one of these things.
That's the microphone.
Sorry.
It's all right.
Sorry, guys online.
Okay.
So in one of the top here, B, so everything coming in and it's getting to that center, it hits that neutron star, and that's down here at D, the neutron star in the center, and bounces off it. It has nowhere to go. And that's where it just blows out at that point. And this is just showing supernova 1987A, and just how big it can get. This is actually a bit.
So
What's
this-
that?
Is that also a nebula, the same thing?
No, it's
No.
not.
What's a nebula?
A nebula is just gas that's surrounding, usually it's either surrounding a star or it's near a star that's highlighting it, okay? So this is actually an image of that supernova, and we take pictures over years. You can actually see the expanding pressure wave coming out from that, because that's what I mentioned before you, the question was asked, so how do we get a new star form? Where do the elements come from? How do they get into this planet of ours? Well, this is how, because that pressure wave is going out, and this is actually, the glow you see here is the surrounding gas that's around there that's getting pressed and heated by the pressure wave that's coming out from that supernova. So that's what we think happened. This is basically the life cycle of our sun. We're about 4.5 billion years. About 10 billion will turn into a red supergiant. By 11, we probably are a planetary nebula. Earth may survive it, may not. It's going to be on the edge, whether we'll make it. Probably not.
But it'll be too hot here
Oh,
anyway.
we'll be a cinder. Yeah, so not going to be too exciting a place to live. And the thing is, there's a whole other talk I have on planets evolve. We think of Earth as a really nice, hospitable planet, but for most of its existence, it wasn't hospitable to us. So planets evolve over time. So,
What was bad about it initially, like volcanoes everywhere, or?
there wasn't even oxygen.
Oh,
There was no oxygen. Okay.
so how did we get oxygen?
Well, there was something called the Great Oxygenation Event that happened, and basically we got anaerobic bacteria came in very quickly after the formation of the planet. So after about 500–600 million years, we actually had life on the planet, but they were anaerobic bacteria, and what they produce is oxygen.
Well, who made them? I mean, where did they come from?
Well, that's a whole nother talk.
Okay.
Okay. So, just a quickie on white dwarfs, because they're kind of fascinating. They're, like I said, remnant, less massive, about 4 times our sun, stop fusing, sheds outer layers. And the only thing keeping a white dwarf from collapsing further is something called electron degeneracy pressure. Basically, electrons want to repel each other. Okay, so it's basically them repelling wholly. Give you an idea, inside of a block of copper, electron degeneracy pressure in a block of copper is 40 gigapascals. That's 10,000 times the pressure of our atmosphere. That's what holds a block of copper to be a block of copper, so it doesn't collapse. So only the pooled nucleus keeps them from escaping. White dwarfs actually have an interesting thing. Basically, they can only get so big because that electron degeneracy pressure keeps them from to any closer, but as you get more and more mass there, it keeps pressing more and more and more. So at some point, you get to a point which is called the Krandaskar limit. It's about 1.4 times the mass of our sun. If you get beyond that, the electron degeneracy pressure cannot sustain it and it's going to collapse down to a neutron star. Okay? The guy who came up with it by this name was a young Indian guy who was coming over to study astronomy, and he was on a boat. It was back around 1900, and he was dreaming this up as he was taking the boat across to actually England, was where he was going to study. And what's interesting about it, this is our planet in the blue here, and then a 0.23 solar mass white dwarf you see here on the left. So not as massive as our sun, it's only about 23% as massive. But the more you get mass, the smaller it gets, because it's starting to collapse it. And 1.3, just almost at that limit of 1.4, you can see how small it gets. So white dwarfs are not very big. So when our sun ends up, it's going to be somewhere about the size of our planet, and yet have the mass of a star. So you can imagine the gravity. These are some white dwarfs that are within about 18 light years of our planet. Sirius B. If you get up early in the morning these days, Orion is out, one of my favorite constellations, and Orion, right near it, is the star Sirius. And it's the brightest star in the sky, and it also has a companion, which is a dead star, a white dwarf, Sirius B. So that's the closest one to us. So we talked about what's going to happen. Here's a red giant star, white dwarf, is sucking off material from that sunlight star that's nearing the end of its life to the dead star, the white dwarf. So then you get that accretion disk forms, you get a bright spot, and that's gonna blow up when it gets enough material to thermonuclear explosion on the surface. It's only on the surface. And it shoots the material out at a fraction of the speed of light, okay? And you get a lot of things coming up. We really want to study this, and this is actually a little video here. There it goes. This is all lead up to the blaze star, the morning star, okay? Okay. So accrete, erupt, and repeat. So they can blow up and they can do it again and again. What's not known is, does that white dwarf get a little heavier every time? Does it blow off all the mass that came on? Because maybe it's heading towards going to become a neutron star, but we don't know. So there's a lot of physics here we don't understand about these things. We've discovered about 10 of these that seem to blow up, and then they, in a certain period of time, they blow up again, then they blow up again. So these basically are the largest hydrogen bomb explosions in the universe. So we really want to understand it because it's really cool physics and help us understand what's actually happening there. So what we're going to use, there's a star, the blaze star, that I'm going to talk about in a second. We're going to use all these different observatories to actually look at this when it goes. Okay? And I'll just go through that. You recognize that as James Webb. I'll just go through it here. So here it is. T Corona Borealis. Okay? This is the northern crown. All right? It's in our summer skies. It's in basically constellation of Boötes here. Here's Corona Borealis, Hercules. You can see the Big Dipper here, Ursa Major. So you get an idea of where I'm talking in the sky. So when you use a letter, normally we use like Greek letters to identify stars, but if it has a Roman numeral letter on it, that means it's a variable star. So this is T Corona Borealis. So you can see it right here. It's just off that bowl. And this star is interesting because it's periodic. It's gone a number of times. It goes from being totally not visible to the human eye by, we could say, magnitude, so magnitude 10. The higher the number, the dimmer it is. Okay, it's the reverse of what you'd like it to be. And it's going to go to about 2.5. So that's easily seen with your eyes. It's gone off before in 1787, 1866, and 1946. Okay? So it's about 2,400 light years away. Red giant's about a little over the size of our sun, but it's big. It's a red giant, so it's about 75 times the size, radius-wise, of our sun. White dwarf, almost at their limit, 1.37. They orbit in about 228 days. But they're separated only for about half an astronomical unit. An astronomical unit is the distance between us and the sun. Okay? 98 million miles. Okay? Excuse me, 93 million miles. And so it's about half that distance. So you're looking more like the distance from Venus to the sun.
What does the T stand for? Where did that come from?
They're letters they put on that basically indicates which sequence did they identify it as a variable star.
Okay, so there could be more
Oh, there's more variable stars in there. But stars can be variable for a lot of reasons. Sometimes it's because of what we're talking about here. Other times it's that they're getting near the end of their life and they're starting to pulse a little bit as they're trying to figure out what they're doing.
Okay. And is this one of those getting near the end and starting to pulse?
This one's already at the end.
Okay, and it's done it before?
It's done it. It's just,
okay.
Yep. So what we're hoping is basically we can do some really good science. This whole thing could be boiled down to, we want to do some good science to understand when this thing goes off. We want to use a number of things to measure it. So what's happening in the star system? This is basically what I'm saying. To your question, this is the dead star in this system. Okay, so it's done doing its job. This star is nearing the end of its life and it's now become a red giant, and it's basically, this material is being sucked onto the star into the white dwarf, the dead one. So it just sits on the surface. Think of it as like a hard ball. And the surface material gets thicker and thicker and thicker and pressing down more and more. And eventually it gets to a point where it can fuse hydrogen to helium and blow. Okay, it's going to blow because there's not enough mass there to do it. So this actually shows it here.
Now, if the star is dead, how is it, what keeps it turning so that it grabs onto the living star?
what happens is that it's like, even if our sun died tomorrow,
Okay,
the Earth would keep going around the sun. Gravity holds it there no matter what. Doesn't have to be doing anything other than it's the mass of it is warping space around it that causes it to stay there.
so it's
That's
gravity.
So it's gravity holding these two stars rotating around each other. One's dead, one's gonna be dead, but not yet dead. And this basically just produces this big area of just material being sucked off, and it's basically gets to a point where it blows. And the question is, why does that keep reoccurring? And, you know, does it eventually lead to that star blowing up in a supernova explosion? So this is what happened. So in 1944, they were tracking the brightness of the star. You can see these are magnitude on the left of the y-axis. So the higher up it is, it's brighter, and lower is dimmer, okay? And then just before, about a year before it went off, there was a dip. We don't know why. Okay, before you ask the question, we don't know why. And then it came, and then it blew, and then there was a little oscillation, and then it went back. And so we said, well, okay, how would that, this is actually the red giant star, as I was saying to your question before, it's pulsing. You can see it going up and down, up and down, up and down. I mean, some of that may be the white dwarf pulling on it, some of it's just instability in the star. So in 26, when we thought we were predicting, in 2016, a sustained brightening of T Corona Borealis was seen.
You
So-
say part of it might be instability in the star. The living star?
The living
or
star.
dead star?
The dead star is dead.
Okay.
It's not doing anything, just sitting there. So in 2016, we saw a brightening of the star. We said, that's a year, that happened 8 years before the nova before. So they predicted, well, in 2023, it's gonna, the star dimmed, was observed in 1945, so then they thought, well, it's gonna go in 24. But it didn't happen. So everybody was saying, coming, nothing happened. Well, bottom line is we only have a very limited set of data. We have May 12th, 1866, and then February 46. We don't really know how consistent that is, but we think it'll happen anytime. Now, based on these two data points, probably it's an 80-year period, not what we were saying before. So it should happen, as far as we know, probably next year, okay, in 2026, okay, that's going to blow. So basically, we're thinking it could go, so that's basically what we're thinking. The dimming was seen, but, in March, why was it predicted? But we don't know. There just wasn't enough data to do it. So what you want to consider is keep checking for the eruption. There's sites you can go to, but you're going to hear it on the news. When this thing goes, it's going to be, there's a new star in the sky. And it's going to be kind of cool. This constellation is really easy to see. So if you just learn like some basic structure of where Hercules is and where Ursa Major is, then you can find Corona Borealis. And keep looking for that to see if there's a new star just off to the left down here. And that's my talk. So,
Thank you.
you're welcome. Happy to take any questions with regards to this topic or anything else about space.
How do you determine the age of a star?
There's a number of ways of doing that. Basically, you can look at the surface temperature of the star. You can also sometimes do it by trying to understand the mass that's around it. But generally, there's theoretical models that are used to try to estimate the age of the star. And so we think they're pretty accurate, but we have no way of absolutely proving it. No, it's not a good answer, but that's the best answer I can give you.
Yeah, I heard there was some stars that 100 million years old, and then some they found that were 10 billion years old.
Well, that's what I was saying with like the red dwarfs. Those will live, they're as old as the universe already. Okay, so, close to 14 billion years old. So you can do it in a number of ways to look for try to figure out the age of the star.
There was a supernova around 1054. That was a big supernova. I think it was age.
Crab Nebula.
Yeah.
Yep. Yep. That's in the constellation Cancer. So the Chinese observed it and recorded that. You can see it. It's beautiful. We actually have taken progressive shots of it. You can actually watch it expanding. in space. So it's pretty cool.
How fast does debris travel from the supernova?
Generally, it's about anywhere from like 5 to like 20% of the speed of light. It's moving. Moving.
Anyone on Zoom with a question, feel free to unmute.
We're hoping next year we're going to have the Artemis 2 take a crewed mission around the moon. So hopefully the budgets align and we're able to do that. That'd be great. First woman also to go around in the crew. And then the following years is the plan, is the landing of Artemis 3. A lot to be done between now and then. So I'm not too comfortable with that time. That's me speaking, not NASA.
Is the Artemis going to find out what's going on that dark the dark side of the moon?
Yeah, it's, you know, it was always termed the dark side of the moon only because the moon, when it rotates around, it rotates, but it rotates once when it goes around the Earth once, so we always see the same face. It's not dark at all. It's just the other side of the moon, so we always call it the far side versus the near side. But they are different. The far side has a lot different cratering than the near side. We got a lot more mare over here, or seas, which are big lava fields that have solidified. The other side doesn't. Why? We don't know. There's various theories. Could be that there was a huge impactor that came from to the far side and actually went through most of the moon and then caused basically, you know, liquefaction of the moon and that material coming out onto our side. We don't know. We all should have been astronomers because you sit down and you dream these things, right?
What, are we doing anything to be able to watch out for asteroids and head them off?
We sure do. I have a whole talk on just that topic. But, you know, planetary protection. There's actually a planetary protection division of NASA. There's international groups. There's part coordination with the United Nations, trying to say, can we as nations collaborate on this? Almost 3 years ago now, time's still flying by, there was a mission called DART. Did you hear about that mission? Fascinating mission. I'll give you a quick synopsis. It was the double asteroid redirection test, DART. I always love people who come up with these acronyms. I'm never good at acronyms. And what the goal was to pick this asteroid that is near Earth but not too close to us, and happened to have its own little moon going around it. And we could see it from, with telescopes. It was so far away that we couldn't actually see them, but we could watch the light from them, and we could see it dimming every so often, and the thing went around and brightening and dimming and brightening and dimming. So we knew how long it took for that to go around. We could estimate, with physics, you can estimate the mass of those. And once you've done that, we were like, well, could we launch a spacecraft at that little moon?
To blow it up or something?
Well, we were trying to actually just change its orbital period, how long it takes it to go around. Basically, it takes around 11 hours to go around, and we were hoping to change it by a minute, okay? That was sort of our accuracy of measuring. So we sent this little spacecraft out there. It's about 600 kilograms, which is like, you know, a car. So not much. I mean, that little moon weighs like millions of pounds, okay? So it's big compared to this little thing. But they tried a new form of propulsion on this thing now, so every time we do something, we usually try to do multiple things. So we had this mission, but we said we want to have it powered by ion power. Okay, so basically ion propulsion. So we actually, wasn't normally where you have like oxygen and hydrogen reacting together to produce water, which is a normal like thing, or kerosene, other fuels. This was actually using xenon, and you basically charge it up with an electric field, and then you propulsion, use magnets to push it out. And what they did was, it's not much force, but it was going the whole time, and so constant acceleration for a year. So by the time it actually got to this asteroid, it was going about 15 miles per second, okay? So it was really moving. And the thing is, this asteroid is so far away that it was like 3 to 4 minutes of light time between us and them, so it had to be autonomous. We'd never seen the surfaces. The big one, the little one that we were targeting was too small, so we said, you go first, you go into the big one, and it's going for the big one, and when you see the big one, Now we want you to go and find the little one, then you aim for the little one. There's a video of this, I can't show you now, but it's amazing to watch. You can Google it. And this thing just flies by this big one, and you can see all the rocks on the surface. And then you can just see it pulverized right in the center of that little moon going around. It hit it right in the center. It actually, before it hit, it jettisoned off these little, like, sort of about this size little CubeSats, we call them. They're about this big. And this one was made by Italy, and basically was watching the thing, and you could just see it just like, it was incredible. But these things, weren't sure whether they were solid or not. Turns out they're like rubble piles. And so we were hoping to do 1 minute change. We did a half hour. So it was very successful. So we can shoot at something, we can hit it, we can make a change. So it's all about the long-winded answer to your question is, if we have enough time, and we actually, as humanity, coordinate, so we have rockets ready to go and do stuff, we could nudge something. If we have 10 years, we give a little push, little push, little push. So we don't want what happened to the dinosaurs. They didn't have the ability we have to see these things coming in. But we know they're coming. We've actually, all the big ones that are like dinosaur killers, we know basically 90% of those. We're pretty confident that we know those. And so far, there's nothing in the next 1,000 years that's going to hit us.
So hitting the little one just changed its course? So
Speed. Basically, took some energy off it, so the period, it went closer to the big one. So we just changed it. That's all, that was the goal, just to
that
see.
kept it from hitting us?
Well, it wasn't actually, it never was going to hit us. This was just a proof of concept to the question of, can humanity actually try to do it? There's different ways. One technique is called the impactor, which is what I just talked about. You just wham it. Another could be gravity. You could shoot, if you had enough time, you could have a very massive spaceship that would be near an asteroid, and just that gravity, you could pull the thing over time, keep pulling it away from the Earth. If it's far enough away, you only need a fraction of a degree, and it'll totally miss the Earth. Okay. Another would be nuclear. Now, if you ever saw Armageddon,
Blow it up.
yeah, Armageddon. Well, that's the question. Not what they're trying to do. Armageddon, where what's his name? Who was the actor in that?
And flat, and that's like Bruce Willis.
Bruce Willis.
Yeah.
Drilling down. Of course, Bruce dies in the end. Blah blah blah. Very very touching. But it's totally what you don't want to do. Okay. The last thing you want to do is take something, because picture I'm coming at you as a big rock, and then you blow me up. Now I'm a bunch of pieces just coming at you. You haven't changed the rock at all. So with a nuclear approach, if we only have like a year or two, that's pretty much the approach we got to use if it's big enough. Then the idea is you want to go close enough to it that the explosion, and you basically melt one side of the asteroid, and basically all those particles will come off, and that acts like a rocket and just pushes the thing away. Okay, you don't want to make it into a shotgun coming at the Earth. That'd be horrendous.
What will we Google for that dart? Sorry, so we can Google that.
You can Google that video. You want to see it.
What
So,
will we Google? What will we?
just do NASA DART mission.
Dart mission.
You Google DART mission, and then look at the video,
Cool.
and you'll be like, oh my God, this thing is incredible.
So it's NASA darkness, what else? Is it just NASA darkness?
No, DART, D-A-R-T.
D-A-R-T.
Right, double asteroid redirection test. So, yeah, that's, and like I say, it had to all be autonomous, because we couldn't wait for the light time between us and it was already minutes. And it would be over by the time we actually could send a signal to it. So the technology is just astounding when you think about it. You're shooting at something you can't even see,
That's
and you're moving at 15 miles per second, and you're trying to aim at this little spot, and they did it.
There's some talk about something that's coming towards the Earth now, or is that just some hokey web?
There's always somebody claiming that, there's something coming to us. There's things by us all the time. If you go to a really cool website, you want to see a really neat one, NASA put together this website called eyes.nasa.gov. And you go on there, you could go, one of the things, I don't know if I can do it here. We have access to the web?
Mm-hmm.
Let's see if I can do this. Which browser do you like?
Doesn't matter.
Get this off the screen, hide that. Okay. Eyes.nasa.gov. So this is a 3D simulator that is totally accurate. And so it'll show us, like I'm going to show you right now, the asteroids around our planet. They can track every one of these, and there's millions of them. Okay, so let's take a look here. You can do this at home. Eyes on the solar system. It's loaded. You want to have a nice high-speed internet connection. So this is the real positions of the planets versus each other. You can zoom in and out. And I want to show asteroids. I don't want to see an asteroid. That's not so exciting. Give me a second here. Of course, every time I want to show this live, it's not going to work the way I want to. Where are the asteroids? Let's go back. Oh, I gotta go over here. These two. Eyes, NASA, asteroids. Eyes on asteroids. Sheesh. Yes, this is it. I'm scrolling down. All right, there we are. See it? All those blue dots are asteroids.
Uh-oh, we're in trouble.
Yeah, so you can see here's Mercury, here's Venus, and then Earth is right over here, I think. Right behind Osiris-Rex, but this blue one's us. So you can see where it is. I can put these in motion so you get an idea. All these are being tracked.
Holy smoke.
Yeah, and I can actually, you can get an idea. Here's the solar system. Just went through it. Is this sweet or what?
Yes.
So here's Earth right here. And you can see some of these really big asteroids. So Osiris-Rex is a big one, crossed right over the path of the Earth. Now, it didn't happen to be passing us at the time the Earth was there, so it's not a problem. Eros is another one. Bennu is one that is thought in about a century will get close enough to us that Earth's gravity will nudge it enough that about 20 years later, it has about a 0.1% chance of hitting the Earth. It sounds pretty low, but then the example people like to do is say, well, the odds for a pro golfer hitting a hole-in-one is about the same. And there are golfers who have done 5 hole-in-ones, okay? So you start sweating it a little bit. So there's a whole thing called the Torino scale where we rank how dangerous an asteroid is. Right now, all of them are zeros. There was one you may have heard of like last year that got everyone excited because they first get a measure on and they don't have enough data, and they started saying how close could it come to Earth. It looked like it was coming right at us. So it went up to a 3 on that scale, which is pretty significant. And then when they gathered more data to say where exactly is that thing and how exactly is it traveling, it turned out it wasn't even going to come close. So it's not an exact science when they first get it, but the news media love it. Okay. Something coming at us. Could die tomorrow. But this site, if you want to play and have fun, you can go and explore all the planets. You can follow our missions. You can go, one of the fun ones is to go on the Lunar Reconnaissance Orbiter. You can sit like you're almost right on top of the thing. And it's rotating around about 50 miles over the surface of the moon. And the actual surface of the moon you see is real. It's the real image of the moon. And you're just going over it and you're seeing the structures. It's just incredible.
What's that one called?
That's EYES, EYES.nasa.gov.
No, for the moon one. You want to?
Lunar Reconnaissance Orbiter.
Okay, thank you.
LRO. And the Earth stuff is, I haven't even talked about, but we have satellites that are looking at our planet too. So you can look at those, and those are accurate images of our planet today, and you can just see it. But again, have high-speed internet, please, because you'll be sitting there for a while waiting for it to load. Okay. Most people don't know about this, but it's a wonderful site. I have a whole talk, I just use that and just talk about amazing things.
You've got a lot up here, brother. I
I-
give you a lot of credit for that.
Thanks.
I mean,
I've worked at it for a long
I'm sure
time.
you did, I'm sure you did.
But been a great audience. Any more questions? Glad to answer them.
Thank you very much.
You're welcome.
Okay.
Thanks for coming.
Thank you.